can you solve this math challenge? And the question goes like this. Find the value of this infinite sum 1 over 5 squared plus 3 over 5 raised to the 4th power plus 6 over 5 raised to the 6th power plus 10 over 5 raised to 8th power plus 15 over 5 raised to 10th power, and so on and so forth, wherein this phi is a golden ratio. Now, you can pause this video if you want to give this problem a try. And now, let's answer this question together. But before that, I will show you the answer to this question. So the value of this infinite sum must be equal to just pi, or the golden ratio itself. Now, what is the solution to get this answer? Alright, so first thing we need to do is to let this infinite sum be equal to a variable, and let's call this as s. So we have s equals 1 over 5 squared plus 3 over 5 raised to the 4th power, and so on and so forth. Now, what we're going to do is to multiply both sides by 5 raised to the 2nd power, or 5 raised to 2. If we do that, we get 1 over 5 squared multiplied by pi squared, this becomes to 1. 3 over 5 raised to the 4th power multiplied by pi squared, this becomes 3 over 5 raised to the 2nd power. 6 over 5 raised to the 6th power multiplied by pi squared, this becomes 6 over 5 raised to the 4th power, and so on and so forth. And now, what we're going to do is to rearrange some terms a little bit, and we need to subtract this first equation to the second equation. Now, if we do that, we have pi squared times s minus s on the left-hand side, and on the right-hand side, we have something like this. Because 1 minus 0, this is just 1, alright? Also, we have 3 over pi squared minus 1 over 5 squared, this becomes 2 over 5 squared. And also, we have 6 over 5 raised to the 4th power minus 3 over 5 raised to the 4th power will give us 3 over 5 raised to the 4th power, and so on and so forth. Now, let's focus on this result. So we have now 5 squared times s minus s equals 1 plus 2 over 5 squared plus 3 over 5 raised to the 4th power plus 4 over 5 raised to 6 plus 5 over 5 to the 8, and so on and so forth. Now, let's simplify the left-hand side of our equation. Let's factor out this s. If we do that, we get s multiplied by 5 squared minus 1. Now, recall that the definition of phi, if we have 5 squared, it is equivalent to just the value of phi plus 1. Now, if we subtract 1 on both sides, 5 squared minus 1 must be equal to just pi. Therefore, 5 squared minus 1 right here is simply equal to just phi. And s multiplied by phi is simply equal to phi multiplied by s. Alright. Now, what we're going to do is to multiply again the whole series, the left side and the right-hand side, by pi raised to the 2nd power. So, if we do that, we get something like phi cubed times s on the left-hand side, and on the right-hand side, we get something like 1 times pi squared, we have phi squared. 2 over 5 squared times phi squared is just 2. 3 over 5 raised to the 4th power times pi squared, so this becomes 3 over 5 squared, and so on and so forth. Now, again, what we're going to do is to rearrange some terms a little bit, and we need to subtract the first equation to the second equation. And if we do that, we get on the left-hand side, we have pi cubed multiplied by s minus phi times s. And on the right-hand side, we have pi squared minus nothing, this is just pi squared. 2 minus 1, this is just 1, right here. Now, 3 over 5 squared minus 2 over 5 squared, this becomes 1 over 5 squared. 4 over 5 raised to the 4th power minus 3 over 5 raised to the 4th power, this is just 1 over 5 raised to the 4th power, and so on and so forth. Alright, now let's focus on this result. We have now phi cubed times s minus phi times s equals phi squared plus 1 over phi squared plus 1 over phi to the fourth power plus 1 over phi raised to 6 and so on and so forth. Now again, let's simplify the left-hand side of our equation. So we can factor out phi multiplied by s. So if we do that, we get phi multiplied by s multiplied by phi squared minus 1. Again, using this identity, phi squared minus 1 is simply equal to just phi. So this is equal to just phi. Now, phi multiplied by phi is simply equal to phi squared. So we have phi squared times s. Alright, now on the right-hand side, take note of this series. We have 1 over phi squared plus 1 over phi raised to the fourth power plus 1 over phi raised to 6. This sequence right here, or this series, is simply a geometric sequence. Wherein, if we have a geometric sequence wherein the value of r is between 0 and 1, this simplifies to just the first term over 1 minus the common ratio r. Or simply, this infinite geometric sequence can be written as the first term over 1 minus their common ratio. Now, we know the first term. This is just 1 over phi squared. And we also know the common ratio. Again, this is just 1 over phi squared. So, this infinite geometric series can be written as 1 over phi squared over 1 minus 1 over phi squared. Now, let's simplify. The denominator becomes phi squared minus 1 over phi squared. So, we can cancel out phi squared on the denominator of the numerator and the denominator on the denominator. So this simplifies to 1 over phi squared minus 1. And this is equivalent to this whole geometric or infinite geometric sequence. And now we have something like phi squared multiplied by s. This is what we want. Equals phi squared plus 1 over phi squared minus 1. Again, let's simplify this equation. Phi squared minus 1, we know that this is equivalent to just phi. Now, to eliminate the denominator phi, let's multiply both sides by phi. Alright, so phi multiplied by this, multiplied by this, multiplied by this, or the whole term, let's multiply this by phi. This will give us phi cubed multiplied by s equals phi cubed plus pi plus 1. Now, what is the value of phi plus 1? Now, using this identity, if we add 1 again on both sides, we get the same result as pi squared equals phi plus 1. So, pi plus 1 is simply equal to pi squared. So, we can replace this with pi squared. And now, on the right-hand side, phi cubed plus pi squared, we can factor out phi squared. If we do that, we get phi squared multiplied by the quantity pi plus 1. And again, we know pi plus 1 is simply equal to phi squared. So this can be replaced by pi squared. Now, phi squared multiplied by pi squared, this is just phi raised to the fourth power. And to solve for the value of s, let's divide both sides by phi cubed. And using some laws of exponent, phi raised to the fourth power over phi cubed is simply equal to just phi. And that is the value of s. Therefore, this infinite series that is set to be equal to s, and we get that s is also equal to just phi. Therefore, this infinite series must be equal to just phi. And that is our answer. And as always, we are done.